Previously, we've looked at the theory behind Richardson's extrapolation and the related Romberg. Today, I want to look very specifically at an example. I want to look at the integral from 1 to 2 of 1 over x with respect to x. We all know from Calculus 1 that the exact value of this is natural log of 2. I want to calculate the right end approximation for this using n equals 1, 2, 4, and 8 subintervals. The reason that I want to do this is I want to make 100% sure that my approximation method is doing what it's supposed to be doing. And secondly, I will use these approximations when I look at Richardson's extrapolation. For n equal 1, delta x will be the width of the interval, 2 minus 1, which is 1, divided by the number of subintervals, which is 1. Delta x will be 1. I'm going to use as my representative function value on this one subinterval the function value at x equals 2, the right end. The function value for f of x equal 1 over x at that point will be 1/2. So if you multiply horizontal by vertical, you'll get 1/2 for an answer. When I do the right end rule with only one subinterval on this problem, I should get exactly 0.5 for an answer. If I have two subintervals, I'll take the interval from 1 to 2, which is of length 1, I'll cut that in half. My delta x will be 1/2 now. In contrast to what we did before, we now have two subintervals. There are two right ends to worry about. My right end rule approximation will be 1/2 times the function value at the right end of this interval plus the function value at the right end of this interval. The function value for the first will be 1 over its right end, 1 over 3/2. The other will be 1 over 2. And after you do the arithmetic, you'll find out that the approximation is 0.58 and then an infinite string of 3s in exact arithmetic. The n equal 4 case is done similarly. Delta x will be 1/4. Since everything is going to be involving fourths, I'll write the start. I'll write the 1 as 4 over 4. The next point's 5 over 4, 6 over 4, 7 over 4, 8 over 4, of course, is 2. I have to look at the right ends of the subintervals. I have to look at the function at this point, there, and there, but not there. 1/4 times 1 over the reciprocal of 5/4 is 4/5. The reciprocal of 6/4 is 4/6, and so on. Putting these in my calculator, I got 0.6345238.095. I don't want to round these numbers in any way. If I rounded this and I said, oh, it's 0.64, when it comes time to compare what comes out of my computer program with my hand calculation, that would be of no value to me. And finally, we do the same sort of calculation, except we use 8 subintervals instead of 4. The computation is exactly analogous. There are some right ends of subintervals. Those are the places where I'm going to evaluate the 1 over x function. And after doing all the calculations, I get 0.6628718504. And as we said a moment ago, we don't under any circumstances want to round these things. I've written a couple of pieces of code to look into these things. First and foremost, I have to make sure that my right-end rule approximation function is working correctly. So we'll take a look at that. By now, much of this should be very comfortable to us. I've got myself a module. I'm using G4trad. So setting the precision kind to 8 means double precision. In Silverfrost, you probably would do 2 there. I'm going to have a program, an integer n, real, kind equals L, A, B, right. I set the beginning and ending of my region of integration to 1 and 2. In my function right, what I send it is n, a, and b. So on these 4 lines here, I'm going to print out my approximation based on only 1 subinterval, followed by the approximation based on 2, and then 4, and then 8. These are the things that we calculated by hand. We know what we should get out of this. My function that I'm going to integrate is 1 over x. Now, there's going to be an issue that we'll need to talk about. That 1 over x, 1.0 over x. X is a double precision variable. Most modern compilers, when encountering 1.0 divided by x, will interpret that to mean the floating point version in double precision of the number 1.0 divided by the double precision value in x. Here is my function right. I'm going to do the right end approximation. We've talked our way through this thing and similar things quite a few times, so I'm going to be brief here. I feed it in the beginning and end of the region of integration. Also, I send it the number of subdivisions to use. Delta x in our mathematics, dx in our code, is b minus a divided by, I convert n's value into a floating point value of the appropriate kind, b minus a over n. There are n subintervals. I'll list them 1 through n. X will be the right end of the current subinterval. I have to add up all of the function values that I get for my right ends and multiply the sum by delta x. That will be my approximation. If you look back at the handwritten work that we've just done, it should be fairly clear to you that I'm just writing a program to do exactly that work. So let's compile and run this thing. If you look at the numbers that we produced previously, you'll see that these numbers are those numbers up to rounding errors. And in this case, the rounding errors, for example, in the second one, you have an error in 2 digits at the end. So since double precision is usually accurate to 14 or 15 decimal places, you're getting roughly 13 digits correct, which is a clear indication that the routine is doing what it's supposed to be doing. Now, I've made a couple of variations on this. In this one, I'm going to allow you to tell the computer how many rows are going to be in your table of numbers. I'm going to store all of these initial approximations into column 0 of the table T. This is the setup that we were using for the Newton form of the interpolating polynomial. I'm going to have the beginning and end of my interval. In init is going to be the number of subdivisions to use at the beginning. And what we'll do is we'll set that to 1. Initially, n is equal to that. I could have set n init equal to 50 or something if I wanted, but I want to do it with 1 so that I can check my numbers again. I'm going to go down column 0, and every time I have a position in that column, I'm going to calculate the right-hand rule at n subdivisions from A to B. After I do that, I'm going to double the number of subdivisions and go around and do it again. So initially, I'm using 1 subdivision. The next time, n will now be 2, so I'll be using 2 subdivisions. The next time after that, n will be doubled again to 4. The next time after that, I'll be using n equal 8. So when I print out column 0 of the table, it should be those same numbers that we got both by hand and in check 0. Nothing else has changed in the program. F of x is 1 over x, and this was my right-end approximation rule. If you look at the numbers, you will see, as they should be, they're the same ones we got before. In the next version of the program, I put in just a little bit more output. I print out all of the columns, the approximations that I've got, and I'm going to print out the error. And here's a tricky point. The true solution is supposed to be natural log of 2. I've got it written here as 2.0 d0. That's 2.0 times 10 to the 0 power in double precision. You could also say real kind 2, comma, kind equal 8, or whichever one you're using. I want to see what influence that literal constant 2.0 d0 has in terms of the error. And as you can see, things are going just great. In column 0, the errors were on order 10 to the minus 4, 10 to the minus 5. When you go to column k equal 1, suddenly the errors have dropped to 10 to the minus 8. Down at the bottom, they're already down to 10 to the minus 10. The next column, the errors are 10 to the minus 14, 10 to the minus 15, something like that, and you have achieved full double precision accuracy. If we wanted to make our code fancier, we could check and see if a new column differed in relative sense from the previous one by no more than some small multiple of 10 to the minus 15. If that's the case, there's no sense in going on because you're done calculating. So this is excellent. This is very good news. What I'm wanting to point out with that too, though, is you have to be careful about the 2. By doing it this way, this is sort of the old-fashioned way of forcing that 2.0 to be 64-bit double precision. Here's another way. Real 2.0 kind equal this L value. And as you see, that produces the same results. But the thing you have to be careful about, and the thing that trips many people up is what if you just did that? Oh, I'm going to have extra parentheses there. What if you just did that? The 2.0 is not being stored into any variable, so the computer would have to guess, do you mean 32-bit version of 2.0 or 64-bit version? Or if you go by the letter of the standard, 2.0 not being used in an assignment is going to be interpreted as 32 bits. So you're going to calculate the natural logarithm of the 32-bit version of 2.0. You're going to subtract that away from something, and you're going to contaminate that something, which has 64 bits of accuracy, with something that only has 32 bits. Keep in mind, the numbers in the T table have not changed in any way. The only thing that's changed is how I'm doing the logarithm. If a person didn't know any better, they would get tricked by that and think they're only getting 9 digits of accuracy, when in fact, the numbers that are coming out of the computer are actually accurate to 14 or 15 decimal places. So if I'm using an ASCII string that represents some floating point number, and I want it to be double precision, I have to tell the computer that. Most compilers have a way of defaulting to one precision or the other, but either way you do it, make sure that the constants that you're putting in are what you think you're putting in. Words. The natural log of 32-bit number is not the same as the natural log of the 64-bit number, so be wary of that. Coming up soon, we will talk a little bit about double integrals, and then we will resume our discussion of the initial value problem for ordinary differential equations. I hope everyone's doing well. I'll talk to you again soon.